Good afternoon, students. Your last week I have given important questions in block 1 and block 2. So today we'll see some important questions in block 3 and also block 4 and some of the topics in block 3 and also block 4. So last week up to that is block 2 we have completed all the important questions. Even I hope I have given even block 3 also. That is block 3 is about the Riemann integrability. I have told the introduction. 7, 8, 9th unit. That is the Riemann integrability conditions, mean value theorems of integral calculus. And also unit 9 is about the fundamental theorem of integral calculus. These three are the units in block 3. So I have given some definitions. Introduction of how to show that a function is Riemann integrable. Those conditions I have told. And what is the infimum, what is the supremum, and the lower Darbox sum, upper Darbox sum, lower Riemann integral, upper Riemann integral. So these all topics I have told. So based on these topics, you will get the all the theorems. So even in this unit, you have some important theorems. That is one of the theorem is Darbox theorem we have. So statement and proof is important. And next theorem, important one for 10 marks is conditions for Riemann integrability. Okay. So the necessary and sufficient condition for a real valid bounded function f to be Riemann integrable over the interval a comma b, that is a closed interval a comma b. Okay. So the statement will be a bounded function f mapping from a comma b to r is Riemann integrable if and only if for any epsilon greater than 0 there exists a partition p of closed interval a comma b such that u of p comma f minus l of p comma f is less than epsilon. That is upper Riemann integrable minus lower Riemann integrable. Whatever the value will get, that will be always less than epsilon. So epsilon is a it is an arbitrary constant, always positive, which is greater than 0. Next, one more in 93 page number. That is every continuous function is Riemann integral. So this is the 5 marks question you will get. Show that every continuous function is Riemann integrable. So continuous function, we know the definition which you have learned in that is a SEM 1. SEM 1 it is there. So which function we will call as a continuous function. Okay. So if you remember the definition, whatever the function is there, continuous function, you have to show that every continuous function will be a Riemann integrable, means it satisfies the conditions here. Whatever the value will get for UPF, that is upper Riemann integral, and also lower Riemann integral, you will get the same values. Then only we call a function to be Riemann integrable. Okay. So that you have the statement is there and also proof is there. Next 7.3.3 theorem, that is f mapping from a comma b to r is monotonic on closed interval a comma b, then f belongs to r, that is f is Riemann integrable. So we have to show that every monotonic we have seen in sequence. Okay, there we have learned what is a monotonic sequence. So here whatever the monotonic sequence we have, function is there, that is a non-decreasing. So with the help of that, you have to show that it is Riemann integrable. Next one example we have that is the 95 page number 7.3.5. So this one means to show that a function which is given in the form of f of x equals to x square, we have to show that it is Riemann integrable. Means you have to find here lower Riemann integral, upper Riemann integral, what is the infimum, what is the supremum values. Then if you get both the values as the same, then we call that whatever the given function is there, that function is Riemann integrable. Okay. Even this example also we have seen 7.3.6. Okay. That is, let f be defined on closed interval 0 comma 1 by f of x equals to 1 if x is rational and it is equals to minus 1 if x is irrational. We have to show that f is not a Riemann integrable. So whatever the upper Riemann and lower Riemann values are there, those you are getting as both are not same. Okay, by this we are completing, that is seventh unit about the Riemann integral. In this one more check your progress problem is there, that is every constant function is Riemann integrable we have to show. So that proof is given in page number 97, 7.3.4. So in unit 7, block 3, first you see all the definitions. After that, you see the theorems here. 7.2.13, Darbox theorem. 7.2.13. Okay. Next, second one is 7.3.1. 7.3.1. Okay. Next is 7.3.2. Next is 7.3.3. Okay. And even fifth one, 7.3.4. Okay. So in any rare case, you will get 7.3.5. And even 7.3.6. Okay. These two are 10 marks questions. Okay. And whatever these are there, these are the 5 marks questions. So only these two, that is the 11th question, 11th A question will be from this one. That is any, this is the Darbox theorem. This is the necessary and sufficient condition for the Riemann integrability. So these two you may get for 11A. Okay, 11th A question. So these are the 5 marks questions. So from these two, anyone compulsory you will get for 10 marks. So if you go to the 8th unit, in 8th unit is the fundamental theorem of integral calculus. Okay. So whatever the heading you have, the same problem will be given for 10 marks question. Okay. So here one remark is there. This is also after the remark you have an example problem is there. So this is also important. 8.2.4. 8.2.4. Next. 8.2.7. Okay. This is very important. This you will get for 10 marks question. That is a fundamental theorem of integral calculus. Okay. So from 1/8 unit, you will get only one question that will be for 10 marks, or this question you may get for 5 marks question. And even 8.33 also important. Okay. So one question you may get for 10 marks question from the block 3. So now if you'll go to the unit 9, it is a mean value theorem of integral calculus. In this only 5 marks questions you will get. So in ninth unit, 9.2.1. Okay. Second one, 9.3.1. Once this question has been asked for 5 marks. Okay. This is for 5 marks. Integral as a limit of sum. Next, third one, 9.3.6. So whatever the example problems are there for solving the limit as a sum. So try to practice them. From that you will get any one question for 5 marks. 9.3.8. Sixth one, that is 9.6. First question A and B. Okay. 9.6. First question A and B. So these are the important questions in block 3. So I have told the problems from this one, and even introduction of the Riemann integrability I have told. So next if we'll go to the block 4, it is the sequences and series of functions. So in this unit 10 is about the pointwise and uniform convergence. Pointwise and last 12th unit, last class I have told the, that is the problems I have told on power series. We have find the interval of convergence and also radius of convergence. So in 10th and 11th unit, you have the concept of pointwise and uniform convergence. Okay. So just we'll see the introduction of what is a pointwise and uniform convergence. Block 4, unit 10. Okay. First we have the definition of what is the sequences of functions. It is just the sequence of function. Okay. Sequences of functions. Okay. So if you know the concept of what is the sequences of function, in the third, that is a fourth unit, we have studied what is the definition of the sequence and also how we'll write the sequence and how we'll represent the sequence Those concepts we have seen there. Okay. With the help of that, whatever the concept you have learned there, here we use the same concept of that is the sequence. So how we will represent that one? So we come across sequence of functions like this. That is fn of x such that n equals to 1 to infinity. Okay. As we know, we'll write the function as like this, such that we'll take it in the if you'll write as like this flower bracket also, we call it as a sequence. Okay. But this is, we call it as a sequence of functions. Here function is fn of x. So that fn of x is defined as like this: x to the power of n is equals to 1 to infinity. Okay. So here fn of x is a function. It is defined as x to the power of n, where n value is from n equals to 1 to infinity here. Okay. So if we'll take n value as 1, what you'll get? We can take like this: if n equals to 1, 2, 3, so on up till. So what will be f1 of n value? You are taking 1, no? F1 of x is equals to x to the power of n. F2 of x is equals to x square. F3 of x is equals to x to the power of 3. F4 of x is equals to x to the power of 4, so on like this. Okay. This, whatever how you are writing here by taking n value equals to 1, and whatever the function you are writing, that whatever the pattern you are writing, we call it as a sequence of functions. Here n will be defined, and even whatever the x value is there, x value will be also given there, in which closed interval or in which open interval x values lies, that will be also given in the question. Okay. With the help of that, you have to write the sequence of functions here. So whatever the values you are writing, that if you write here, what will happen? It is x to the power of n, comma x to the power of 2, x to the power of 3, x to the power of 4, so on up to. So this, when you are representing these all function values as here, this is called as sequence of functions. Okay, sequences of functions we are writing. So we have the definition in our textbook. X to the power of n equals to 1 to infinity, defined on a subset, defined on a subset S is equals to whatever here S is given as a set, no? So this S value is whatever the values we are taking for X. Okay. So X values will be from open interval 0, comma 1. Okay. So here, whenever we are writing n value as 1, we are taking you may take x value as some 0 point something. Whenever it is an open interval, means whatever the two end points are there, they will be not included in that set. So after 0, whatever, after 0 and before 1, whatever the real numbers are there, those real numbers will take as x value here. And here n values are from 1 to infinity. So here whatever the n is there, n will be always a natural number. That means 1, 2, 3, whatever the counting numbers are there, those are the small n values. But here whatever the set is there, that set is the real numbers. Okay. So that's why we'll write here a subset or equals to R. Okay. S is a subset such that it is equals to open interval 0, comma 1, which is subset or equals to capital R. Capital R is the real numbers. So for each n belongs to capital N. Okay. N will be always, it will be natural numbers. So fn of x equals to x to the power of n. So here this is the function we are defining in the form of x to the power of n is a function on S. Okay. So thus the above function, thus the above function thus the above function above sequence, sorry. So thus the above sequence has functions as entries. Just now I have told you f1 of x, f2 of x, like that, whatever we are writing, that as we are writing above sequence as functions, and hence is called, a sequence of function. Sequence of function on yes, on which we are telling it is on the set yes. Okay. So how we'll define that one means for x, for a belongs to open interval 0 comma 1. Okay. For a belongs to open interval 0 comma 1, we have fn of a. Okay. Fn of a n equals to 1 to infinity is equals to a to the power of n is equals to 1 to infinity, which is subset or equals to capital R. That means here wherever we are taking in place of x, we are taking the value as a. Here s was the set, no? So we are taking one element. So s equals to open interval 0 comma 1. So from the set S, you are taking one element as A, which belongs to open interval 0 comma 1, such that in place of x, we are writing that point as A. So whenever we are writing as x means here the function, whatever it is defined, you are writing as a to the power of n equals to 1 to infinity. So whatever the function here defined from the series sequence of functions, that values will be subset or equals to real numbers, capital R. So this is the definition of sequences of functions. Is a sequence of real numbers. So is a sequence of, you are able to see it. Is a sequence of real numbers. Okay. So whatever the function here we are defining, the function we are defining as a form a to the power of n. Okay. So this, whatever the function defined as a to the power of n, it is convergent sequence. If whatever the value of this a to the power of 1, it is tending to 0. If the values it is tending to 0, then we call the sequence as a convergent sequence. Okay. And in page number 117, you have the definition. Thus, for a given sequence fn of x n equals to 1 to infinity of functions defined on the subset, and for every fixed a belongs to S, we may study the convergence of the real sequence. So this sequence is called pointwise convergence of the sequence. So if you know the concept of what is the sequences of functions, then we can know that what is a pointwise convergence. Here the point we are taking it as A. So whatever the function is there, it is defined at the point A such that we call it as a pointwise convergence. Okay. So this, whatever the defined sequence is there, no, this is the defined sequence from the function. It will be convergent to 0. Okay. This is also important one. So whatever this sequence is there, this sequence, that is a n x n equals to 1 to infinity. is convergent to 0, is convergent to 0. So in this case, we say then we say the sequence, then the sequence, whatever the function is there, fn of a n equals to 1 to infinity, n equals to 1 to infinity, fn of x, okay? Fn of x, n equals to 1 to infinity is convergent pointwise to 0, pointwise to 0 at x equals to a. Okay. So just now we have defined, we have taken one point small a which belongs to open interval 0 comma open interval 0 comma 1. Okay. So there we have defined the sequence of functions. So in that, just now I have told when whatever the sequence is there is convergent to 0. Okay. Whenever it is convergent to 0, we say that the sequence fn of x. Fn of x is whatever the function we have defined in the starting. So that function is, we call that function is convergent pointwise to 0 at x equals to a. Okay. So this value will be tending to 0 whenever this x value is a. So therefore, it is called as convergent pointwise to 0 at x equals to a. Okay. Next, in this only we have the main important one in this unit, that is a pointwise convergence. Okay. So that definition, if you know, you can do the proof of some theorems depending on pointwise convergence. So you have definition in page number 117, that is 10.2, that is pointwise convergence. Pointwise convergence. Okay. So here we have let S is subset or equals to capital R, A belongs to S, and Fn is mapping from S to R, be a function for all n belongs to n. We say that the sequence of functions converges pointwise at x equals to a to a real number f of a belongs to R if and only if for all epsilon greater than 0 there exists n naught belongs to n such that for all n greater than or equals to n naught. So here the definition of uh, convergence we have, no, that is fn of a mod minus fn of a mod less than epsilon. That is the main thing is here let S is subset or equals to R. Okay. And whatever the point small a is there, it belongs to set S. Okay. And if Fn is a function which is mapping from S to R. Okay. Fn is a function which is mapping from S. S is a set which is subset of R. So S, if you think S as a subset of 0, comma 1, so whatever the elements are there in this, those are mapping with the real numbers capital R. Be a function for all n belongs to capital N. Okay. The sequence of function, the sequence of function, the sequence of functions, that is Fn n equals to 1 to infinity, converges pointwise So it just now we have seen, no, it converges pointwise at x equals to a. Okay, at the point x equals to a, to a real number, f of a belongs to capital R. Okay, this symbol, you know, it is if and only if. Okay, if the condition is that if and only if for all epsilon greater than 0, there exists n naught belongs to capital N. Okay. So here n is there, whatever the element here is there in the function, it belongs to natural numbers. Similarly, we are defining one more, instead of n, we are defining n naught, which also belongs to natural numbers n, such that for all n greater than or equals to n naught. Okay. So whatever this n value is there, this value is greater than this n naught value. Okay. So my pointwise convergence definition is that Fn of A minus f of A, okay, is less than epsilon. Okay. This is the main condition we'll have whenever the sequence of function converges pointwise at x equals to a. That is Fn of a minus f of a, which is less than epsilon. Okay. If whatever this statement is there, if this statement is false, we say that the sequence diverges pointwise at x equals to a to f of a. Okay. So if this statement is satisfied, and if the statement whatever is given, it is satisfying this condition, that whatever the function we are given in the question, if it is satisfying this condition, then we say that the sequence of converge, whatever the functions is there, they converges pointwise at x equals to a. If this, whatever the condition is there, it is not satisfied, then we say the sequence of functions diverges at the pointwise at x equals to a. Okay. This is the main important one. First one, if this statement, if this statement is false, we say that the sequence, we say that the sequence, what is that sequence? Fn, n equals to 1 to infinity, diverges. Then the sequence Fn, n equals to 1 to infinity, diverges. This also diverges pointwise at x equals to a, to f of a. Okay. So now we have the definition for the main thing, that is a pointwise convergence. So whatever the main definition is there, from that we can shortcut and we can tell that if at every x belongs to s, the sequence Fn is convergent pointwise to an function where f is mapping from s to r is a function, we write that how we'll represent the pointwise convergence means limit n tends to infinity, Fn of x equals to f, or limit n tends to infinity, Fn of x equals to f of x. Or means representation here, different types of representations are there. Three types we can represent. And the last one, important one, usually we use in the theorems is that Fn is tending to f. This is also called pointwise convergence. Okay. So main thing is, this is the main, that is a representation of pointwise convergence. This is the main important definition, okay? Definition of pointwise convergence. And this is the important. Whatever this condition is there, this condition is useful in solving even the problems also. Okay? This is the important one. If you know this concept, in problems and also in solving the theorems, you can use this one. Oh yeah, the main thing is that if at every x belongs to S, the sequence if at every x belongs to S, the sequence Fn 1 to infinity is convergent pointwise to an f of x, where f is mapping from S to R. Okay, f is mapping from subset S to R. Okay, is a function. So we write first condition is, we'll write it as limit n tends to infinity fn of x equals to f. Okay, so this is the representation of pointwise convergence. Or second one is that limit n tends to infinity fn of x equals to f of x. Okay, for all x belongs to S. This is also pointwise. Okay. Next, or third representation is Fn is convergent. This whatever the symbol is called, this is as a convergent. Okay. Function Fn is convergent to F. Pointwise on capital S. So this is the three types we are representing the pointwise convergence. So usually in theorems and problems we will use the third one. Okay, that is Fn is convergent to F. So whatever the Fn function is there, that is converging to F pointwise on subset S. So you can see one example problem, 10.2.1. So here the function is defined as x by n, where n values are 1, 2, 3, 4. And Fn of a is equals to a by n, as n takes arbitrary large values, a by n tend to 0. So a by n in the sense a values are 1, 2, 3, 4, no? So 1 by, that is 1 by 1 means you will get a only. Next you will get a by 2. Next a by 3. Like that all values it will be going on and they will be tending to, 1 by n sequence will be compulsory tending to 0. So it is, whenever it is tending to 0, that means the whatever the function is given, it is a pointwise convergence function. Okay. Fn of a equals to 0. That only proof given in the textbook. That is 117 page number 10.2.1 example problem. Okay. So some example problems are there in the textbook. Check your progress also, you can see. Next one, important one is the uniform convergence. So the unit itself is about the pointwise convergence and also uniform convergence. So you have the definition is there. What is mean by uniform convergence? So here F1 pointwise convergence means Fn of a minus f of a value will be less than epsilon. So that main thing you have to remember. Fn of a minus f of a value, modulus of that will be less than epsilon. If you see the uniform convergence, Let S is subset or equals to R and Fn is a function defining from S to R such that small n value is belongs to capital N, that is a natural numbers. The sequence of function Fn converges uniformly to a function F if and only if epsilon greater than 0 there exists. Here the difference between the uniform convergence and the pointwise convergence is, in uniform convergence, whatever the function is there, that function will be convergent at the point itself. But pointwise convergence, you will have one certain point. That point is x equals to a. So at x equals to a point, the given function is convergent here. But in uniform convergence, the function itself, we are telling that it is epsilon it is less than epsilon. Okay, that is the main difference you can understand here. Uniform convergence. So uniform convergence is let S subset or equals to R and Fn is a function mapping from S to R, be a function, for each n belongs to n. Okay, that is n belongs to natural numbers n. The sequence of functions, what is the sequence of function? Fn, n equals to 1 to infinity, converges uniformly to a function, f mapping from S to R. Okay. So this Fn mapping from S to R be a function for each n belongs to n. Then the sequence of functions, that means from here function, if you write the sequence of function, then they converges uniformly to a function, different function here. What is that function? F is another function such that which is mapping from S to R. Okay. So what is the condition? So this function to converge to this function, the main condition is that, necessarily and sufficient condition is that, if and only if for all epsilon greater than 0, there exists n naught belongs to n such that for all x belongs to S, we have Fn of x minus f of x is less than epsilon. Okay. This is the difference between pointwise convergence and also uniform convergence. There, Fn of a minus f of a we have written. What is that a? A is a point which belongs to subset here S. Okay. From there, that's why this function is convergent function at the point x equals to a. Here point is not there, just we are writing the condition. What is the condition? Fn of x minus f of x less than epsilon for all n naught, n always greater than or equals to n naught, n belongs to n. Okay. So we write, we will represent this one. This is limit, we write as limit n tends to infinity, Fn is equals to f. Okay. So this is the representation of uniform convergence. Uniformly. Or a representation of same. A pointwise we have represented, no? Fn converges to f. and we read it as Fn converges to F uniformly. You can see this definition and explanation in page number 120. That is 10.3, uniform convergence. So if you know the pointwise and also uniform convergence, based on those two definitions, you have the theorems are there which you will get for the 10 marks question. Okay. That is a 12th A question or 12th B question you may get from this one. So 10.4.1. Now I'm giving the unit 10 important questions. That is the okay. First one is, see the definitions here. Whatever the definitions I have told, just to go through them. Ten point two point one. 10.2.2 and 10.2.5. Okay, from these three problems, any one problem you will get. Next, 10.3, fifth one. 10.3.4, 10.4.1, and the eighth one, 10.4.5. This is also 5 marks problem you may get. One is 10.4.6. So these example problems are important. So try to practice those all example problems. So these are the important questions in 10th unit. So if you'll go to the 11th unit, it is the infinite series of functions. So infinite series of functions means, just now we have seen the sequences of functions, no? Here the series of functions will be there. You can see them in the page number 130. You have the explanation is there. So unit 11, important questions are 11.2.3. This is regularly asked question, and 11.2.1, 11.2.3. Okay. 11.2.1, 11.2.3. It is a problem you have. Next, 11.3. This is very, very important. Okay. That is a waste stress M test. 11.3. Okay. So this is regularly and continuously asked question for 10 marks, 11.3. Okay, statement and also proof will be there. In page number 135, you have one example problem will be there. That is 11.3.2. 11.3.2. So that will be asked for the combination of the weight stress M test. Next 11.3.3. So it may be asked for 5 marks. Okay. This is the 10 marks question. And this, whatever the problem is there, example problem, this will be for 5 marks question. So you can see the example problems here, exercise problems are there in 136, page number 11.4, 11.4, third question, 11.4, 2, okay, take like this, 2, 3. Okay, second question, third question, and also fourth question. 11.4, that is exercise, we have second and third and fourth questions. So these may be asked for 5 marks, or sometimes it will be asked for 10 marks question also. So this is the important questions in, that is 11th unit. So same one you can see in MEQ questions are there, 11.7. Okay. So you can say 11.7 here, 11.7. So 1, 2, 3, 4. So how the question is framed, you can see from the MEQ questions. That is, first question is about the continuity, that is 11.2.1. And second question is the weight stress M test. And third and fourth questions are the problems. Whatever you have in your textbook, those problems are there here. Okay. So this is the MEQ questions you have. This is about the unit 11. Next, if you go to the unit 12, 12.2.1. Okay, 12.2.1, 12.2.2. So these are the theorems you have. 12.3.4. Okay. So this 12th unit I have told, last class problems I have told. That is how we represent the power series. I have told that one. You can see in the last one. And here 12.3.5. Okay. This a problem I have told. And 12.4 we have. So these are the exercises we have. 12.4.3 you can take. 12.4.3 A, B, and C. Okay. Whatever the exercise problems are there, those all. Next to 12.4.4. These are also exercise problems. That is A comma B comma C. So proofs already you have in your textbooks. Just you can see and you can solve them. Okay. Next exercise is there 12.5. There you have 1 and 2. 1 and 2. Okay. So finding the radius of convergence and also interval of convergence. So by this we are completing the 12th unit also. These are the important questions I have told, and almost whatever the 4 blocks are there, in 4 blocks we have covered some of the important problems and also important definitions we have seen. From that you can solve the, that means you can do the uh, theorems, whatever the theorems are there, you can write the statement and also you can write the, all the questions will be given. So here this real analysis is a theory part, as I have told in the introduction. So compulsory theorems will be there. So theorems, it will be asked to write the statement and proof. Okay. So from starting you first block to fourth block, I have given the important questions and also whatever the problems are there, I have told all the problems in first unit, first block, and also second block, even in the third block, Riemann integrability, and the last block also we have seen. Okay, so this is the last class. So already we have completed the 8 classes we have completed. So you can see all the classes and you can follow whatever the topics I have told. Okay.